So when most people hear the word radiation, we usually think of things like cancer or nuclear, like a nuclear bomb, or danger, destruction and power, right? That's true, but that's actually just a small part of what radiation is. In fact, radiation is so much more than that. Radiation is the light that you're seeing off the monitor that you're watching this coming into your eyeballs. And it's also the sound that you're hearing from my voice through whatever way you're listening to this video. It is. Radiation is, like, that's sound and light radiation. Radiation is everywhere. It's all around us. It's fascinating, I think. And because it's all around us, we use it to figure out how things work and why things work. And that's why it's information. Radiation is information. So why don't we start with the physical definition of what radiation is? And radiation is the emission or transmission of energy. Basically, the release of energy, if that makes sense. And energy is the capacity to perform work, but basically energy is to make things happen, right? To make things work and make things happen. So for example, you need food energy and water energy to keep your body functioning, right? As well as other things. For electricity, for this camera, there needs to be electrical energy going through it to make it work. It's pretty cool. So radiation's all around us. There's 4 types of radiation. There is particle radiation, which exists in the form of alpha and beta particles. There's also sound radiation, like acoustics. There's also light radiation, which is part of the electromagnetic spectrum. We'll talk about that later. And the last one, which is the newest, gravitational radiation, which is in the form of gravitational waves. Now, radiation can go through a medium, so it can go through things like air or a solid object or water, and it can also go through a vacuum, so the vacuum of space where there's nothing there. There's 2 types of radiation. There's the harmless radiation, which is fine for us, and there's also the harmful radiation. The harmless is called non-ionizing, which basically means this type of radiation doesn't have enough energy to actually be harmful to the body or to any living organism, where ionizing does. And what it actually does, ionizing radiation, is that it actually rips part of atoms off. So it actually rips electrons off your atoms or off atoms of other things. That's the process of ionizing in physics. Pretty bad. Let's talk about non-ionizing radiation, the harmless radiation. And we'll begin with acoustics or sound radiation. So these are just sound waves. And if you can picture this as like a person's face and that's the mouth, then these sound waves just come out like that. They go through like that. They propagate like that. And all they are just little atoms that bump into each other and bump all the way along. And eventually those atoms will go into our ears, and then that signal will go into our brain, and then our brain will interpret what that signal is. And that's how we hear sound. Isn't that cool? I think it's cool anyway. Now, they only go through a medium, which means they can only go through air or water or solid. They can't go through the vacuum of space, because in space, there's no particles, or there's very few particles. It's a vacuum. That's why there's no sound in space. All right, let's briefly talk about gravitational radiation, because it's pretty complicated. Gravitational radiation, as far as I know, is harmless to us, and it comes in the form of gravitational waves. And these are waves that exist in space and time itself, and they're based on the mass. So if you stick with me, with objects that have mass, which is you, me, pretty much almost everything we know except for light, they actually create a gravitational influence. They do in space itself, which that influence is represented by like this black curve. So the smaller they are, the less mass they have, not really smaller, but less mass, the less of the influence. Now what happens is if these 2 objects interact, they actually create little ripples on this influence, they do. Or if they collide, they make even bigger ripples. And these are only tiny. I don't know if you can see it. It's not a smooth line, like it's a bit bumpy. Those are gravitational waves, and we can detect them with massive objects colliding. Remember, these things are tiny, so even with massive objects like 2 black holes, the most massive objects in the universe, these waves are still tiny. They're still like little fluctuations, smaller than atoms they are. It's crazy, it is. It's amazing that we've been able to detect them. I hope that was okay. Jeez. So the last non-ionizing radiation form that we'll talk about, so that's the harmless radiation, is electromagnetic radiation, or light. but not all light. It's just radio waves, microwaves, infrared and visible light. Now, if you don't know, light is part of something called the electromagnetic spectrum because it's electromagnetic waves, electromagnetic radiation. So light isn't just the light that we see with our eyes. It's actually things like microwaves, the thing that heats up your microwave. It's infrared, so heat, right? It's also UV, so the UV light that comes from the sun, that's a type of light. And it's also radio waves, which are the things that broadcast TV signals or make Bluetooth work or Wi-Fi. All these things are part of the same thing of light, and they're harmless to us. And the reason why they're harmless is because they don't have enough energy to be ionizing. Remember, going back to energy and ionizing. They don't have enough energy to actually rip electrons off atoms and be damaging. So if you hear things like 5G and all that, harmless. Now, the reason why they don't have enough energy is because they have a low frequency. And the frequency is basically how frequent the wave comes past in a specific period of time. So for this wave, which has a lower frequency, you can see there's not a lot in that specific period of time. Where here, there's a lot, right? So it's more frequent. And frequency is directly related to energy. Don't worry about the H, that's just a constant. But that shows you that low frequency equals low energy, which equals non-ionizing radiation. Now, remember how we talked about not all light being harmless to us? Well, why don't we use this to transition from non-ionizing radiation to ionizing radiation, from harmless to harmful. And we'll start with the high frequency light. So things like ultraviolet, X-rays, and gamma rays. These lights have a higher frequency, and because they have a higher frequency, they have a high enough energy that they can actually damage your body. That's why with ultraviolet light, out in the sun, we can wear sunscreen or sunblock to protect us from getting burnt by the sun. With X-rays, that's why X-rays or X-ray examinations are really short. The actual image is very short because you don't want to be exposed to X-rays for too long, because it can cause radiation sickness and other things. And with gamma rays, well, they're not good for anything. Fortunately, we don't have a lot of them around, but yeah. Why don't we talk about them? Just a side note, radiation sickness is where you're exposed to ionizing radiation, a lot of it, in a very short amount of time, and it can be very bad for your body. No, bad. Gamma rays. Now, gamma rays are the highest frequency of light that exists, which means they have the highest energy. And these are very hard to shield from. They're very dangerous. In fact, they're so hard to shield from that if this was a whole block of lead, like that long, and I shot a gamma ray through there, you probably wouldn't be able to shield it. They're pretty crazy, they are. Now, fortunately, we don't have many on Earth, which is great news for us. The majority of gamma rays produced in the universe come from cosmic events. So they come from big events like supernovas, so exploding stars. But they can still be produced in a nuclear bomb and a few other instances, but fortunately we're pretty safe on Earth. The other form of ionizing radiation we're going to talk about, or the other form that exists rather, is particle radiation, and that comes from a process called radioactive decay, where a heavy element, so heavy, when I say heavy I mean a lot of mass inside this element, so a lot of atoms inside, a heavy element actually needs to shoot part of it out. It needs to eject part of it in order to maintain its structural integrity, in order to keep itself together. And it can either shoot out a helium atom or an electron or a positron in the form of alpha and beta particles. Now, alpha particles are very easy to shield from. You can shield yourself with just like a piece of paper, fine. And beta particles, they're a little bit harder to shield from, but like a thin piece of aluminum should be able to shield you from them. And there you go. That's ionizing radiation. Alright, that's a wrap. See you later. Now, you can go if you want, but we're going to quickly summarize what radiation is, right? Radiation is the emission or transmission of energy, and it comes in two forms. It comes in non-ionizing and ionizing. Ionizing being the harmful ones that most people have heard about, but also non-ionizing, which is the harmless ones, which is the radiation that you're using to see me and listen to me right now. It's light, it's sound, it's all these different things. It's the information. Like we're seeing the light that we get, our brains interpret it, we gain information. Same with the sound. Same with even just looking at things, we gather information about it. That's why it's information. It's so cool. The field of astronomy, where you study space and study everything in space, What they do is, well, they use the electromagnetic radiation and also gravitational radiation now, but you look at things and you figure out, and you just take photos, you just get the light from them, and you can figure out what they're made of, how far away they are, how old they are, and what's happening with them, and so many other things. It's fascinating. It's so cool. That's radiation. That's why it's information. Well, hope you enjoyed. If you have any feedback for us, please let us know. We'd love to hear from you, and all the best. Take care.